This video is about electric potential. I want to compare gravitational potential to electrical potential. So let's look at the gravitational world first. If we look at, let me draw a little pen here. If I look at an object in the gravitational world, this object has to have mass. So what would happen to it in the gravitational world is it would accelerate in this direction. So again, this object has to have mass. If I were to look at the electric field lines in gravitational potential, they would look like this. Remember, they go in the direction in which the object is going to experience a force. Now, this object is going to experience a force due to gravity of F sub g. Okay, and if I look specifically at the equation of the force due to gravity near the surface of the Earth, it's the force due to gravity is equal to the mass times g. And remember, we call this the gravitational field. Now, let's look at the gravitational potential energy and where it's highest and lowest. So if we can imagine this as being ground level, then where would we expect to have the highest gravitational potential energy? Well, we would expect high gravitational potential energy to be right here. And we would expect to have low gravitational potential energy down here towards ground level. Okay, and again, we would expect this object, which has mass, to accelerate downward. So it's going to accelerate in this direction. So let's write down the fact that it's going to accelerate. Well, these are all things we should know about the gravitational world. Now let's compare the gravitational world to the electrical world, okay, and how that relates to its electrical potential. Well, what I have here is I've got two different plates. I've got a plate that's positively charged and a plate that's negatively charged. And I'm going to look at a positive test charge. So if I take a positive test charge right here, it's going to experience a force in this direction. And likewise, just like in the gravitational world, it's going to have electric fields that point in the direction of the positive test charge. Now, this object will also accelerate in the direction of the electric field. I want to say it accelerates in that direction. And the equation here for it is going to be this, for the electric force. Q stands for the charge, and E stands for the electrical field, or the electric field. That should be review. We covered that last time. Now, similar to the gravitational world, where would we expect high electric potential energy? Well, we would expect high electrical potential energy to be here. So we would expect high electrical potential energy in this region. And where would we expect low electrical potential energy? Well, likewise, we would expect a low electrical potential energy here. But this is for a positive charge. If I had a negative charge, let's say it started here, we would expect it to accelerate in this direction. For the negative charge, where would we expect to have high electrical potential energy? Well, the high electrical potential energy for the negative charge would be here. That's for the negative charge. And there would be low electrical potential energy here for the positive charge. Okay, now let's look at how this relates to the electric potential. So the electrical potential is based on a positive charge. Okay, that's going to be really important, so let's remember that. So let's start off by asking ourselves, how do we define electrical potential? Okay, electrical potential is going to be defined this way. V stands for volt, and it's equal to the amount of electrical potential energy per unit charge. And we'll use a symbol here for a test charge. Okay. The unit for the electrical potential is volts. And the equation that we would use would be this. The fact that the electrical potential energy is equal to the charge times the potential. The way that's written for the AP test is like this. U sub E, which would stand for the electrical potential energy, is equal to QV. So that's really the equation that we want to use there. Okay. Now, how do positive charges move? Well, as we saw, a positive charge is going to go from this region to this region, and we know that it's going to accelerate. Now, if I take the amount of electrical potential energy, we said that this would be a region of high electrical potential energy, and this would be a region of low electrical potential energy. But because the electrical potential is based on the positive charge, we would also say that this would be a region of high potential. Remember, the symbol for electrical potential was V. And so this would be a region of low potential. So V stands for potential. This is a region of high potential, and this is a region of low potential, because for a positive charge, this is the region in which there's a high electrical potential energy, and this is the region where there's a low amount of electrical potential energy. And the definition of electrical potential energy is the amount of electrical potential energy per unit charge. So therefore, I would have high potential there and low potential there. So if I look at a negative charge, as we said, would go from there to there and would accelerate. But because everything is based once again on the positive charge, the negative charge accelerates from a region of low potential to a region of high potential. So to answer the question, how do positive charges move? Well, positive charges accelerate from a region of high potential to a region of low potential. To answer the question, how do negative charges move? Well, negative charges move, or they accelerate, from a region of low potential to a region of high potential. Again, the reason for this is everything is based on the positive charge, and the positive charge determines that this has got high electrical potential energy, and therefore this region here has a region of low electrical potential energy. So now we have to define what an electron volt is. Okay? An electron volt is the work required to move a single electron through a potential difference of 1 volt. So if I've got a negative electron, or if I got an electron, I'm just going to use that symbol, and I just let go of it, it's going to go from here to there. Remember, it's going to go from a region of low potential to a region of high potential. Okay? That's if I just let go of it. I can take that same electron, and I can do work to it. I can take it from that region and make it go to that region. Okay? So I would have to do work to make it go from there to there. Okay? Or if I let an electron go, it would just on its own go from there to there. Let's calculate how much work or how much kinetic energy is gained by doing this. And the way we would do that is by using our new equation for determining the electrical potential energy from Q, the charge, and the electric potential. So in this case, my electric potential energy is equal to Q. Remember, the charge of an electron is negative 1.60 times 10 to the minus 19 coulombs. Okay? If I go from a region of high potential, now this V is really a delta V, so that would translate to V final minus V initial. So let's say let's say this is the situation we're interested in. So our electrical potential energy would be equal to negative 1.60 times 10 to the minus 19 coulombs times a V final of 0 volts. That's my final potential minus my initial potential of 1 volt. So I'll have negative 1 times negative 1.60 times 10 to the minus 19 coulombs. So my electrical potential energy would actually equal 1.60 times 10 to the minus 19 joules. So this is the amount of work we needed to move this electron from this region of 1 volt to a region of 0 volts. We're saying that we need to think of electrical potential as being similar to height in the gravitational world. So on this side, I'm going to take a 1 kilogram object and I'm going to drop it from a 10-meter height. I've dug this big old hole 10 meters below ground level, so let's call this ground level. And I want to know how far, or I want to know how fast it's going when it gets to the negative 10-meter mark, assuming it's dropped from a height of 10 meters and has an initial velocity of 0 meters per second. So at the beginning, I'm going to have some gravitational potential energy. I'm going to use my bar graph. And then at the end, I'm going to have kinetic energy. I'll just use a symbol K. So I know that this energy is going to be conserved, so I'm going to say the gravitational potential energy is equal to the kinetic energy. The gravitational potential energy equation is mgh, and the kinetic energy is 1/2 mv squared. I will have to solve this equation for V, which I know we can all do. So the important thing here is to understand that this H is actually going to be a value of 20 meters when we calculate this. Let's look at how we would solve a similar problem in the electrical potential world. Well, first of all, let me fix something here. These M's should be V's. So here's what we're doing. We're taking a 1 microcoulomb object, and we're dropping it, or we're letting it go from a 10-volt region, and it's going to get to a negative 10-volt region. When we let go of it, its initial velocity is 0 meters per second. So similar to our gravitational potential problem, let's look at how we would set this up. At the beginning, all the energy would be electrical potential energy. So once again, we use our bar graphs. And at the end, we would have, once again, kinetic energy. So again, all this energy is going to be conserved. So the electrical potential energy would be equal to the kinetic energy. The equation we have for electrical potential energy now is QV, and that's equal to 1/2 mv squared. Once again, we're solving for V. I know we can all do that, but let's make sure we know what to solve for this V, the potential, the electrical potential. That value would also be 20 volts.